So Romain Meyer is going to speak. So yeah, he's on. So please share your screen.
Yeah.
And there
right.
you go.
There you go.
Yep.
Okay. Thank you very much. I'd like to thank the organizer for giving me the opportunity to talk. It's been very nice yesterday and today, and I'm sure it will continue to be so. So I'm a finishing PhD student at UCL, and I want to talk to you today about work I did during my PhD on escape fractions of redshift 6 galaxies. So if I'm talking about escape fractions of redshift 6 galaxies, Lyman continuum escape fractions, you're probably thinking about this. So here you have on the plot the IgM neutral fraction history as a function of redshift. And to match this IgM neutral fraction history, you would go usually with an analytical model. You would compute what we call the ionizing photon budget. And so simply you would say, OK, I know the number density of the luminosity density, sorry, of the UV luminous sources. I know their ionizing efficiencies from the UVLF, from measurements at redshift 4 to 5. And then basically you can fit for the escape fractions. And so in doing so, you would say, OK, galaxies, if they did reionize the universe, they would have needed an average escape fraction of 10, 20%. The problem when you do this, it's an average statement. You're not actually seeing galaxies reionize the universe. You just say for this to be possible, they should have 10%, 20% escape fraction. And also it's completely degenerate with any luminosity dependence. So for example, in the paper from Romain, he showed that you can basically fit the same data with pretty much a model with bright sources reionizing the universe with high escape fractions, or a lot of faint sources with low escape fractions. And so today I want to take you through two measurements, which are actually measurements of escape fraction at redshift 6. So the first one is the galaxy IgM cross-correlation. So we'll see how galaxies can actually impact gas that we probe with the background quasars and how we can infer escape fractions from that. And then individual measurements from double-click Lyman-alpha. We talked a lot already today, and how we can actually bring all of this together. So starting with the galaxy IgM cross-correlation, we all think of reionization as these bubbles, this Swiss cheese topology, and we all like to think that galaxies actually power these bubbles. And so if you look at a distant quasar greater than redshift 6, you have the Lyman-alpha forest, or what remains of it at this redshift, and you have opaque troughs and transmission spikes. And so around transmission spikes, you're actually tracing ionized gas, and so there should be galaxies ionizing this gas. So the question is, can we actually measure that correlation between galaxies and Lyman-alpha transmission? And how can we infer escape fraction from this? And so we've written a paper series, and I want to go over the latest result from the third paper. So to do this, we take quasars. So here you have the 8 Lyman-alpha forest of the quasars, about redshift 6, so 5.8 to 6.5. And so we've doing a Lyman break, Lyman-alpha emitter survey with Muse or DMOS. And so Muse is in blue, DMOS is in orange, and you can see all the galaxies what we detect. So we detect the Lyman-alpha emission in the field of that quasar, and the distance from the x-axis is just the distance. And you can see that, for example, in 1030, that's your poster child. You have a lot of transmission spikes, and next to the transmission spikes, you have a lot of galaxies. So that galaxies do reionization, do transmission spikes. But if you look at 2329, it's a completely different story. You cannot do this one-on-one association. So you need some more statistics, and that's why we do the cross-correlation function of galaxies with Lyman-alpha transmission spikes. So we identify the spikes with Gaussian match filter, and then we do this 3D cross-correlation, and we find that around LAEs or LBG, you have an excess of transmission spikes. And that's great because you can see, okay, I target galaxies that are probably traces of other densities, and I see more ionized gas. So reionization actually happening, and you can observe it. But we want escape fraction, right? So let's go further on how we model this. So I don't have time, and I encourage you to have a look at the papers if you're interested. But basically, if you sit down and do the calculation, a single LBG or LAE cannot ionize the gas enough so that you have a transmission spike in the Lyman-alpha forest of the quasar. So you need to take into account that there are many other faint galaxies clustered around what we call the bright traces. And so we have a HOD modeling, and we compute how many galaxies you expect to be clustered around these objects. And so in doing so, you need to fix what is the minimum UV luminosity of contributors. So that's the first parameter of the model. You fix the luminosity-averaged escape fraction, of course, and the host halo mass, because the more massive your tracer, the more galaxy will be clusters, and so the signal is stronger. And this one is fixed, actually, because we more or less know the host halo mass of LA and LBGs, but the two others are actually the parameters we can fit for. So before I show the results, well, there's the title already, but I just want to emphasize we constrain the luminosity-weighted average. So I will treat it as the average escape fraction of all galaxies, but actually if you have some luminosity dependence that you prefer, you can fold it into this equation and compare to our observations. So here is what we find. So what you see is in blue and orange, so these are the posterior. So this is a constraint on the luminosity-averaged escape fraction. And these are as a function of the minimum UV luminosity of the contributors to reionization. And you can see we have this banana basically constraint, which is actually normal. Even if there is a dependence on the signal, the slope changes a bit as a function of the minimum UV luminosity. You're mainly constraining the total ionizing output of all the galaxies around your LAs or LBGs. So you can either have bright galaxies only contributing with very high escape fractions, or faint galaxies, all the galaxies contributing with an average escape fraction of 10–20%, and this agrees very well with the neutral fraction history measurement that you can see here in black. In any case, whatever you choose, they must have greater than 5 or 10% at 2 sigma escape fraction. And so I'm not talking about the LAs or the LBGs. Remember, I'm talking about basically every galaxy that's clustered around our traces. So how do we distinguish between the two cases, faint galaxies dominating, bright galaxies dominating? Well, remember here, the constraint is that if only bright objects were contributing to reionization, they should have on average about 90–100% escape fraction. So let's go and measure the escape fraction in these bright objects and see if they have 100% escape fraction or not. And then we can tell if the faint or bright objects are contributing the most. So how do we do that? Well, hopefully people luckily covered this before me. So we have a lot of Lyman continuum emitters and green peas at low redshift that have double peak Lyman-alpha. And so we know there is a tight correlation between the peak separation of Lyman-alpha and the Lyman continuum escape fraction. So you could go at high redshift and measure this. Unfortunately, the IGM damping wing usually absorbs and kills the blue peak. So these objects are very rare, and we only have 3 so far with escape fraction from 1 to 29%. Well, actually, we have 4 because we have a new one that I'd like to show you. So it's called A370PZ1. So it's found in the parallel field of Abel 370, and it has a strong drop in the Z band, hence the unimaginative name. So it has a very strong break. It has also a 3.6 excess, and this is very exciting because it indicates it's a high O3 emitter, and we've heard many talks on this today. And so photo Z of redshift 8, and we have this very nice double peak that we have seen in the spectra. So this is X-shooter, 6 hours. The peak separation is actually way too large compared to low redshift doublets, so it cannot be this. And we have no additional lines, so we're pretty confident. This is double peak Lyman-alpha at 6.8, and the velocity separation is 100. So with a velocity of 100, velocity separation of 100, what is the escape fraction? Well, the problem is that the low redshift relation from Isotov et al. Basically overshoots in that regime, so we can only have a strong lower limit constraint using that. And the constraint is very strong. It's greater than 59% at 2 sigma. So we have an object that is basically near unity in terms of escape fraction of Lyman continuum photons in the reionization era, redshift 6.8, which is quite cool. You can also, not using the empirical relation, you can compare to static shell models that have been developed for years. So here you can see 3 different models. And if you take, for example, the orange or the blue ones, depending on if you want to fit better the peak or the trough, you get an escape fraction of 90–95%. So I can now go back to the constraint I showed you before. And I can say, well, we've looked, OK, 4 objects, but we've looked at MUV minus 21 objects in the reionization era. And their escape fraction is about 30%, plus minus 30%. On average. And so this is inconsistent at 2 sigma with the constraint that we have from the 2-point cross correlation function. Therefore, the combination of these 2 probes and also the metal IGM cross correlation that is shown here, second paper in the series, suggests that we really have reionization that is dominated by the faint galaxies. And so I hope I have convinced you that these probes can be interweaved and combined together to give nice constraint on reionization. And hopefully in the future, both on the double peaked and on the cross correlation, we will have more data coming from James Webb and ground-based surveys. And I hope also we will have more methods to measure directly the escape fractions at redshift 6, perhaps with the low ionization absorption lines with the LT. Thank you very much.
All right, thank you, Romain, for that excellent talk. Yeah, do we have some questions? Yes. So we'll start with Harley Katz, who asks, the faint galaxies around the massive galaxies can be quenched due to radiation feedback, of course. Do you think that there will be a bias in your F-escape measurements from cross correlations by preferentially selecting environments around Lyman break galaxies?
Yes, so that's an excellent question. Yes, obviously the issue is when you do this, if you take LBGs, especially LBGs, because you're pre-selecting them based on the break, but then you don't look at any break galaxy, you look at them, the ones that you can confirm the redshift of. So you're looking at the ones that are in highly ionized environments, and so perhaps you're selecting indeed the environments where you have the most efficient leakers, meaning the constraint that we have target a subpopulation that is the most efficient leakers in the universe. So I think that's why we have to vary the probe. So LAs are perhaps not the best, but metal absorbers, and then with James Webb, we'll target O3 emitters, O2 emitters, or H alpha. And so hopefully in that way, we can avoid the biases due to having Lyman-alpha as a spectroscopic redshift.
Okay. So Rohan Naidu asks, what is the blue to red peak ratio in your double peaked emitter? From low Z sources, the typical blue to red peak ratio seems to be about 0.3. Could this be a merger?
Right. So the blue to red peak ratio is about 60 or 70%, I think. So, well, we cannot exclude a merger. We can never exclude a merger. However, I can say from the 2D, there is no offset between the two peaks, at least not that we can measure. So of course, this would be very interesting to look at with an IFU. I can also say that on the HST data, it looks very round. It does not look perturbed or elongated. So as far as we can tell, it's not a merger. But of course, the best would be to have an IFU there, of course.
Okay, and maybe take one more question. Fahad Nasir asks, due to fluctuations in the Lyman-alpha 4 sightline, the transmission spikes might not always correspond to overdensity. It could be a hot ionized cosmic void. You consider this when calculating your cross correlation?
So we have a temperature density relation in the model. I'm not sure if that addresses this completely, but you're right. It's not only over density. There, we've considered smaller mean-free path. We've done a self-consistent mean-free path as well, depending on the ionization and the density. I think ultimately the analytical model is good because it gives you a nice estimate of the escape fraction. But ultimately, you really want a simulation, and I really hope we will see from simulators that kind of measurements. I know it's difficult. You need long skewers, and you need to model the galaxies. But hopefully, in the end, that's what we will have.
All right, maybe let's take one more question here from Daniel Scherer. Great talk. Have you been able to detect any other emission lines also to have an independent redshift for the Lyman-alpha line profile interpretation?
No, unfortunately, we don't. We have no additional emission lines, so that's very sad. But the photo-Z is very robust. The break is about 4 magnitude. So even with the Balmer break, it would be difficult. I mean, you can't fit it with a low Z solution. And if it was a low Z doublet, then you would have, or even not a merger of low Z lines, you would have other lines, H alpha or O3 or H beta. So it's really, it's really difficult to imagine this is low redshift. But of course, the next step is having probably ALMA and then James Webb on this.
Excellent. Okay, great. Thank you very much, Romain.